Good afternoon, this is Schweitzer. We're going to run through a little video here which I'm going to call Classroom Practice. This is something that we'll be doing in class, and I've shown some examples of how we're going to do some of this work. So now it's going to be just some classroom time to practice these things, and we'll give probably about 1 hour for people to run through a calculation on their own. These are different from the workbook. The workbook is for you to be working through, but this is something that you should pause the video, absolutely pause the video. So let's recap just some stuff that we did. Okay, so first of all, we have a strong an acid, okay, and you should be able to take an acid with a Ka value, and you should be able to just determine the pH of a weak acid. You should note that if I have initial concentration of this guy, I can write out my expression plus H2O yields H3O plus X negative. Okay? You should be able to plug in your concentration of this guy and solve out for your H plus concentration and then your pH. If you only have the conjugate base, then you have to use the conjugate base reaction. So that would be X negative. That could come in the form of NaX. That's typically what they're going to do. And you got to get to the Na, and it's going to be plus H2O yields HX plus OH negative, initial split ratio N. So if you only have the anion, then this guy's going to donate to here. Yep, that's good. All right, then you have to use the X negative. If you have both of them, then you could use either one. That's important to realize. So if I have HX is equaling to 0.1, and the X negative, or NaX, let's call it, NaX equals 0.1, then yes, you can use either one you want, and you would place the amounts that are right here. We would call this particular concept here, where you have both present, a buffer, just so you know. As long as you have both, we call it a buffer, and they just kind of battle back and forth between the two. We do have a special spot where if these both are the same, we call it the half equivalence, just so you know. It's got a unique little mathematical cancellation. Half equivalence. Half equivalence. Okay. The next part here is, what do we do when we add a strong? Okay, when you add a strong to a weak, then we have a slight different variation here. We have basically a two-step process. First step is going to be the neutralization. Now that is going to completion. This is straight completion and is used just like stoic. And then the final, to get your actual pH, you use equilibrium, which is your hydrolysis equation. And you need to be able to be comfortable with this setup. So for example, if I have certain, let's say, 20 milliliters of just this stuff. This is not a buffer, okay, but 20 milliliters of the HX, and let's write out the reaction. I'm going to have, so I have 20 milliliters of this, and I'm going to add, in that case, some NaOH. You should be realizing that I can add whatever I want of NaOH. But there are some common spots that people tend to ask. Okay. Now the reaction, I'm going to be using base hydroxide to neutralize this. So let's write out the neutralization reaction. HX plus OH negative yields H2O, and 8X negative. Okay, and there is also a spectator on here that I'm not showing. Okay, with Na. So in this situation, I do this in moles. I just showed this example, but we're going to have moles of this guy, so it'd be molarity times liters equals moles, so it's 0.1 times 0.02 equals 0.002. All right, and that's my moles. I always do this in moles. All right, and then I'm going to roll this over. I call it rolling, but really it's neutralizing. For every one hydroxide I add, I can knock one HX to X negative. And once I roll even one of them over to here, I now have a buffer. So again, the most common things would be to move half of it over, that's our half equivalence point, or to move all of it over, that's our full equivalence. It doesn't make a difference how much you roll over. Typically, we would never go too much beyond rolling all of it over. If you have more base than you have actual X and HX, then it's going to roll all this to a base. You'll have excess base hanging out, and that thing's going to be extremely basic because of the excess hydroxides. But either way, so a common volume of hydroxide to add, if the hydroxide, let's say, is 0.1 molar, would be 10 milliliters or 20 milliliters. 10 would knock half of it over, 20 would knock all of it over. Or you could add 5. Okay? You're going to knock a certain amount over. If we had, you would calculate out just using the same formula to figure out how many moles you have, and you would just literally add that right here and just run through your ice table. If we add 10 milliliters, it's going to be 0.001. Marker's not doing the best here. Minus 0.001 minus 0.001, and now again 0.001. This is, of course, our half equivalence point, 0.001, 0.001. But then we have so this is where I have both of them. So this is a two-step process. So now we know how much of our two components we have, and now they're going to start battling back and forth. When I attacked it with the hydroxide, I essentially rolled over some of the HX to the X negative, and that sort of allowed the reverse reaction to start becoming more prevalent. So, now again I have both present. I can use either equation I want. Maybe I use the acid equation. Alright, so HX plus H2O yields X negative plus H3O plus initial stoichiometric ratio end. Plug in your concentrations here. Now again, I do need to get these back to concentrations. I added 10 milliliters of this guy right here, which is half of it. That got me halfway. So my new volume is 30 milliliters, so divide by 0.03 liters and 0.03 liters. Plug your concentration in here and plug your concentration in here. And then of course you solve for X and convert that to pH, which is a typical question. That's our generalization. Now, only thing else we would add in here is being able to represent this in a beaker. So if you have a beaker, keep in mind that what we just did here could be represented by having, let's say, doesn't have many, let's just say I have 4 HXs. Okay, 4 is a common number because it's easy to write out. Okay, and I notice I'm keeping them all together. This would represent the initial beaker. I'm going to add in some hydroxides, and what's my ending beaker going to look like? Well, it looks like I knocked half of it over. It's going to be still 2 of them left, and 2 of them would be looking like this. Okay, so that's my just an overall review of what we did. This is new, just to apply to this. Other than that, let's go through some examples. Okay, again in class we will do this, and then we will give certain amount of time to pause to do these and pause them out. Okay, so go ahead and pause the video here, and I'll give an answer here. So calculate the pH of 10 milliliter 0.1 molar NH3 and 10 milliliter 0.1 molar NH4 plus NH4Cl. First of all, what do you notice about this? Okay, well, I note that I have 10 milliliters and 10 milliliters of 0.1 and 0.1, so these are equal concentrations. My KB value is located on the, I can't see it past the screen there, but my KB is equal to 1.8 e to the negative 5th. You can get that off your page 4 as well, page 5 of your workbook. Alright, so here we go. Okay, so now I just basically mix them together. I don't need this first step. I don't have to neutralize it. I just have the stuff I have. Weaks just start battling back and forth by equilibrium. So it's just going to be, I'm going to use my acid version, NH4 plus H2O yields, this guy's battling towards this guy, NH3, and the plus H3O plus, this guy's battling back. This guy's battling that way. Initial stoichiometric ratio end, this guy is 0. Now, this one's going to have a small little wrinkle to it, but I have 0.1 and 0.1, but I'm having some volumes here. So it would be my actual concentration when I mix them together, it's going to be different. I'm doubling my volumes. So it's M1V1 equals M2V2. And I have 0.1, 10 milliliters. You might see the answer to this already, but looking for the end concentration, and it's 20 milliliters. X equals 0.05. This is my concentration after I mix the two together. Alright, 0.05. And this also would be 0.05. At that point, minus X, not playing a role, plus X, and 0. 0.05, 0.05. You also could make an estimation that since this base is stronger than the conjugate acid, that this thing is going to be basic. The concentrations are equal, and therefore I'm going to be basic. So Ka equals 0.05 times X over 0.05. There's our little shortcut rule at the half equivalence. And my Ka equals the concentration X. And therefore, if I negative log this thing, negative log of this concentration, sometimes, here's a little side note here, they sometimes stick the Ka right in here. So we have this thing here that we call, I don't really like it that much, but it's called the pKa. And this is it right here. This is just the negative log of the Ka. And again, what does that tell us? It tells us that, okay, let's run it through here mathematically. Okay, I need to get the Ka here first of all, so I'm going to do that next here. Ka times Kb equals the Kw. I could have used the Kb version. I didn't. So it's Ka, Kw divided by the Kb equals the Ka. So it's going to be 1.0 e to the negative 14th divided by 1.8 e to the negative 5th. And I get a Ka value which is cursor here. Alright, so it is Ka equals 5.5 e to the negative 10th. Okay, so what does that mean? It means, well, when I negative log this, anytime I negative log the Ka value, it gives me my pKa. And this is going to be, if I negative log this thing, would be negative log of the previous answer is about 9.2. Okay? Now what this is telling me is that, again, when I do my math here, these numbers really don't matter that much. They can change a lot, and the Ka really is controlling things. So this means that my pH, regardless of what this concentration is, regardless of what this concentration, within reason, you're going to be awfully close to 9.2. This is called sort of your, might be called your buffer zone, your buffer area. Not exact. Only time the pKa actually equals the pH is if the concentrations are equal, like we did right here. So this is my answer. This is the pH. Of course, it is basic, as I mentioned earlier. But the pKa is a shortcut that you'll see occasionally. This tells you the general area in which this buffer will sit, real close to 9.2. A little higher, a little lower. If the acid's a little higher in concentration, then maybe this will be a little bit more acidic, a little bit. If the base is a little higher in concentration, maybe a little bit more acidic, but really close to 9. Alright, and that is a little introduction to pKa and also our answer. Alright, calculate the pH of a 10 milliliter 0.1 molar NaOH solution mixed with 10 milliliters of 0.1 molar. Okay, again I have, so now I'm having NaOH, okay, that concentration. I have 10 milliliters of this guy. Now what do you notice about this? Okay. Pause, think about it over, and consider drawing this out. Okay. Pause the video and try it out. Okay, a couple things I noticed about this is that, one, I have equal moles. So I have 10 milliliters, okay, 0.1 molar, 0.1 molar, so I'm going to what we call equivalence. I have all of this stuff is going to neutralize all of the acid over to NH3. Alright, what's the beaker look like? Let's draw again 4 of them. I'm going to draw my anions, 1, 2, 3, 4. NH4 plus, NH 4 plus, NH4 plus, NH4 plus. And I'm adding equal amounts of NaOH. 1 sodiums, and I have 1, 2, 3, 4. Okay. And at this point, my ending beaker would just look like this. I have my fork. Still, all my cations and anions are still there. Okay. But now, this reaction takes place. NH4 plus OH negative yields NH3 plus, well, that guy plus water. So I don't typically show the water molecules, but I would just draw it like this. NH3, 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 NH3. 4 of them. Now again, the last question, just hypothetically, how would you determine the pH of this thing? And in this situation, I would simply say that I would need to use the base equation. NH3 plus H2O yields NH4 plus OH negative. Initial stoichiometric ratio, and I would just put my concentration right here. I would need I know that my actual number of 4, 4, and 4, that 4 is not changing, but I would be in a larger volume, so I need to recalculate that volume concentration. So molarity times mole times volume equals moles. So my original molarity of the acid was 0.1 times 0.01 is equal to 0.001. That's my moles I originally had. And that's not changing. I had 0.001 of this, 0.001 of this. I lost 0.001, and I've done 0. That's how sometimes on an AP rubric they'll show it. 0 plus 0.001, and now I just have 0.001. And I divide by my new volume, which of course is 20 milliliters, 0.02, and this is going to cut that guy in half, in this case. Alright, in this case, would be going from 0.1, cutting it in half. I'm not losing any of this stuff, I'm just doubling my volume. So it should be 0.05 equals 0.05. If that makes sense, then you're really coming a long ways. I didn't lose any, I just moved it from here to here, and I doubled my volume. So this guy is going to be 0.05, and then from that point I'm not going to go any farther. You can determine the pOH and then the pH. Next problem. Okay, calculate the pH of 10 milliliters of this and 10 milliliters of that. Okay, we just solved this question out 2 seconds ago. Okay, so I'm not going to do this one here. Okay, you can try it on your own. Hopefully you did it on the last page. Let's change this one to, well, let's go to the next one here. See what we got. Alright, there we go. That's what I was thinking. Okay, so now let's do 5 milliliters of NaOH. Okay, take a moment, pause the video, and there you go. Okay, so this one here, notice here, as you look at this stuff, what do you notice about this? Well, I'm only knocking out half of it. So I'm at the half equivalence point. This thing should be basic. Remember my KB. My Ka was calculated earlier. Let's do that one, because I have that one right here. 5.5 e to the negative 10th. Alright. 5.5 e to the negative 10th. So this thing is going to be basic again, right? If you're getting used to this, you could move along nicely. But, okay, so I have dumped the two together. 10 milliliters of 5 milliliters and 10 milliliters. Okay, so let's first of all do our neutralization. And then we're going to do our battle back and forth between the weaks. So my neutralization is just NH4. Now I don't even include the C. I'll take that off there. Plus OH negative yields NH3 plus a water molecule. Initial stoichiometric ratio, and how much of the actual do I have? I have molarity times liters equals moles. So it's 0.1 times 0.01 equals 0.001. 0.001. Now you can look at this as being half. Always want to show our work. 0.1 times 0.005 equals 0.0005. And this is typically how they would show it. They would just go on an AP rubric, they'll just go minus 0.0005 to 0.0005, 0 plus 0.0005 to 0.0005. And then divide by my new volumes, which is going to be 15 milliliters. 15 milliliters, so I got 5 plus my original 10 equals 15. So 0.015, 0.015. This is not as linear as we might think. But of course, if you've done this a couple times, you might notice that, of course, at the half equivalence point, we have a shortcut, which you could be jumping to quicker if you'd like. But 0.005, 0.0005 divided by 0.015 equals 0.033. So 0.033, that should make sense. So now we're going to our back and forth battle of NH. Now I use either one I want. I got my Ka here, so I'm going to use that one. NH4 plus H2O yields NH3 plus H3O plus. Initial stoichiometric ratio, and of course this is a buffer. This is going to be 0.033, not playing a role. 0.033, 0 minus x plus x plus x. 0.033 minus x, 0.033 plus x, and x. Alright, so Ka equals, alright, it's just going to be 0.033, 0.033, and we have x. So the K equals x, and of course at this point, my pKa, in fact, equals my pH, and that could be a pretty quick shortcut there. You could avoid all this, and they would be okay with that. You knew that. But for our own sake, and make sure we know how to do it, in this case, it's the negative log of the 5.5 e to the negative 10th, and then of course I think it was like 9.2. Did that just 2 minutes ago. Half equivalence point. Okay. All right, and moving along. I think that's all we got there. Oh, one more here. Okay. So calculate the pH of a 10 milliliters of 0.2 molar NEF. Okay. What do you notice about this? Okay. Again, it's 10 milliliters, 0.2 molar, NEF. Cut this in half. Okay, go ahead, give it a try. Okay, pretty straightforward question here. We just have a base, so again, we're recashing through some of our material. It's just F negative plus H2O yields H3O HF plus OH negative, and it shows below, you can't see it, but the Ka is equaling to 6.6 e to the negative fourth. You could also get that out of your text or your workbook. So I have initial stoichiometric ratio end. This 0.2 goes here. I'm not going to work through this whole problem. You can check your work. It's going to be the Kb equals, I have to use the Kb version, by the way. It's going to be 0.2 times x. It's going to be, let's run this thing through, you can see it, minus x, not playing a role, 0, 0, plus x, 0.2 minus x, x, and x. So it's going to be x times x over 0.2, so that is x squared over 0.2, and you can solve it out, square root it, and the negative log of this thing, and then at that point you can take the POH and convert it to pH. We should be basic. Alright, here we go. 10 milliliters of 0.2 more is added to 10 milliliters of 0.2 more HCl. What do you know about this question? Go ahead, solve the problem out. Okay, so in case what we know here is that we are at equivalence. That they're matching. So all of the F negatives is being converted to HF, being rolled over HF. So in this point, I have to do my two neutralizations, HCl plus F negative yields HF. Okay? And you could do your initial stoichiometric ratio if you want, or just do a simple subtraction. So let's do this here quickly. I have 0.2 times 0.01 equals 0.002, and this is 0.002, this is 0.002, I have none of that, minus 0.002 to 0, plus 0.002 divided by the new volume, which is 20 milliliters, 0.02, and I should get a concentration that is 0.1. You note that all I did was roll it over, doubled my volume, and therefore this went to 0.1. That should make sense. At this point, I have to use my acid equation because I only have acid. HF plus H2O yields H3O plus F negative. Initial stoichiometric ratio end, and this 0.1 goes here, and I'm assuming at that point you can solve all the rest of it. K equals, it's going to be x times x over 0.1. Solve for x, and take the negative log of that thing to get your pH. Alright, another one for you to try. Go ahead, pause the video. Alright, looks like I have little bit different here. I went from a 0.1 to a 0.2. A little bit different there. Okay, so notice this. What do you notice the question is? I went to my half equivalency point. I'm now half the moles. So let's do this again. HNAF negative plus H plus yields HF, and I need to neutralize half of it. I have twice the moles now that I had, because twice is 0.2 more. I should say that I had. I dropped that in half. Okay, so I still have my same 0.002. I cut this in half. But now I left the volume the same, but I cut my concentration half. So a little variation. All right, so we got 0.2 was a 0.002 was my original moles. I got that from the previous problem, right here. And let's just run it through. I should note this is going to be 0.001, and I'm going to lose 0.001 over 0.001. This is now going to be just 0 plus 0.001 is just 0.001 divided by my new volume. And I get still the same thing, 0.02, alright, 20 milliliters. And that's just going to be 0.1. I knocked it out again, half of it out again. So this is my this is half equivalency point. So I knocked out half of it, okay? Double check here. We got you can double check yourself. 0.001 divided by 0.02 and 0.05. Okay, and there we go. This is going to be it's at 0.2 now. I knocked out half of it, doubled my volume. Let's make sure I got that right. And I do. Looks like we got 0.05. Okay. Alright, this guy here also is going to be same thing. And at this point here, you have your same concentrations. Even if you got these wrong, for some reason it seems like it should be different. We're going with it at this point, but I could catch a mistake here. But either way, this is just going to cancel anyways. We have our HF plus H2O yields F negative plus H3O plus. Initial stoichiometric ratio end. This guy is the same as this guy, so they end up canceling. My Ka equals 0.05 times x over 0.05. At this point, we have these canceling, and my Ka equals my x value, so the pKa equals my pH. And that you can solve out. The Ka value, just so you know, is going to be 6.6 e to the negative fourth. If the pKa of this thing, and therefore is negative log of the 6.6 e to the negative fourth. .1. So that would be our pKa here, 3.1, and therefore that is my answer to my question, 3.1. All right. All right, again, just recapping this thing from a non-math point of view. I have 0.02 of this, and I knock out half of it with this guy, which that would knock it down to 0.1. And then I also diluted it in half again to 0.05, which is, again, how I got the 0.05 here to begin with. So that should make sense. All right. There we go. Thank you very much.